Hello again, Fluid Mechanics for the 13th of November 2014. This is class number 24, the second of our two recorded lectures for this week. Let's go over a couple of announcements before we continue with some additional applications of the momentum principle and some examples that I've got lined up for you. So for these announcements, remember that Lab 11 is going on this week, and you need to complete the experiment by Friday. By now, you've already submitted your handouts for Lab 11, the handouts that you've prepared, and you've got until the end of this week to actually gather the data and perform the experiment, and then over the weekend can do the calculations and write the report. Your report needs to be submitted by 11 o'clock on Tuesday the 18th. Then at 11 o'clock, what we'll do is conduct Lab 12 during what's normally our class period. We'll have some time to get additional exposure to WaterGEM's program. We'll solve a couple of examples using WaterGEMs. And then the midterm exam will be at 2 p.m. Homework 6A is due today, the 13th of November, by 11 a.m. The grader is going to be collecting those assignments from the folder in my box that's marked 318. So slide your assignment into that folder. He's going to take the folder out of there and start his work grading right at 11 o'clock. Now here's the new homework set, homework set 6B, as you can see on the screen there. That's due by 2 o'clock on Tuesday the 18th. And so you need to have that completed at the same time that we are going to begin working on the exam. A bit of information about the exam. As with the first midterm exam, you're allowed to prepare an equation sheet to help you. The coverage for the exam is chapters 4, 5, and 6. So there's a lot of information that's going to be included on this exam. It's not comprehensive for the whole course. I won't be specifically asking questions on chapters 2 and 3, although there obviously are principles that you learned in chapters 2 and 3 that are still applicable throughout the rest of the semester. So with that said, if you have any questions about these announcements, please feel free to send me an email. I'll do my best to respond. Today we're going to continue talking about the momentum principle and work some examples that will help you understand a bit more how to solve these homework problems. So let's begin with that.
So remember that when we have a pipe that's cut with the control surface, that pressurized fluid that's on the outside of the control volume acts as though it's an external force. And so in the example we worked in class last time, the pressure and the cross-sectional area together accounted for a force that was pushing the control volume towards the right. And when we worked through the example to find what force is required to hold the system steady on that flange, it was actually to the left, because the force of the pressure times the area was greater than the momentum force. And in this case, the momentum force, since the velocity out is so much greater than the velocity in, that would ordinarily mean that for out minus in, out is to the right, in is to the right, so these are both positives. But we have a higher velocity here going out. And so the forces required in this case took into account both the pressure forces and the momentum forces. A vein, yeah.
Like on a couple of homework problems, why is this going to provide a force on the control surface, but this homework problem for it?
Which homework problem do you mean?
Specifically the last one. Jet, like just like the last. Why is that water coming up?
Is it the wedge of water, that jet? All right, it's because all of it was just a jet that is open to the air. And so, it comes out of like a tank or something like that. And as soon as it comes out of it, it's just a jet of air that doesn't have any pressure. And so where we drew the control surfaces was around that wedge. And so that the jet isn't pressurized any longer. In this case, when we drew the control surfaces, the right side of the control surface includes the jet, but the left side of the control surface is cutting through a pipe that is still pressurized. And so here we didn't have to think about, well, what's the pressure in the area, because the jet doesn't have any pressure. As soon as the water exits the tank and is in contact with the air, it instantly loses its pressure. All right, let's work through this vane example. We've got a water jet with a speed of 6.6 meters per second And the mass flow rate is defined, and it's simply changing direction by a fixed vane. This is actually going to be pretty straightforward because there aren't any pressure forces that have to be accounted for. It enters with only flow in the x direction, and it exits with flow both in x and y. But it's going to be relatively simple here. It won't be the combination of any other fluid mechanics principles. We start off by knowing that the mass flow rate is 11.3 kilograms per second and that the velocity is 6.0 meters per second.
In this example, we have a vane, meaning that there's a piece of metal, some other material, that's deflecting a fluid jet. So the fluid jet is impacting this and is changing directions, and it exits with a different angle than it did before. The information that we're given that there's a 30-degree angle between the horizon and the downward direction that this jet of water exits the vane. The water is 6 meters per second, and we're not given any information about whether it's slowing down, so we assume that actually it has 6 meters per second as it enters and also as it exits our control surface. We are given the mass flow rate as 11.3 kilograms per second. And it's asking to find the force of the water jet on the vane. So we have to be careful because normally when we solve the momentum equation, we're solving for the force required to hold the system steady. But this is asking for the equal and opposite reaction. So when the time comes, we'll keep that in mind. First of all, let's apply the momentum principle in the x direction. So momentum in x. Alright, in the x direction, we have the sum of the forces in x are the mass flow rate out, the velocity out in x, minus the mass flow rate in, times the velocity in x. Alright, in the x direction, there is both in and out. So this is the flow that's going in through the control surface, and here's the flow that's coming out through the control surface. The force required to hold the system steady in the x direction will be the mass flow rate. And since the mass flow rate in and out are the same, we can simplify the equation just to the velocity out in x minus the velocity in x, like that. So the magnitude of the velocity is 6 meters per second for both of them, but the velocity out, we want to find just the horizontal component of that 6 meters per second. So that when we make the substitution, it's going to be 11.3 kilograms per second. Now the velocity out in x is going to be the velocity of 6 meters per second. It's a positive 6 because it's still to the right in the x direction. But we have to multiply that by the cosine of 30 degrees in order to get the component that's in the x direction, and then subtract the velocity in x. And the velocity in x is 6 meters per second. That's a positive value because it's to the right. So the force required in the x direction is negative 9.08 newtons. This cosine of 30 is 0.866, meaning that the flow in is going to give us more momentum than the flow out in the x direction, and that's why it's a net negative value. So that's a force to the left to hold the system steady. So if we were holding the system steady with an external force, it would need to be this way. The force would be to the left. Now we're not yet finding the force of the water on the vane. We'll do that at the very end once we've solved things for the y direction. And let's do that. Momentum in y direction. Alright, the sum of the forces in the y direction, it's the mass flow rate out, the velocity out in y, minus the mass flow rate in times the velocity in y. Now in the y direction, we have flow out vertically, but no flow in vertically. Remember that this is our x direction, and this is our y direction, and you can see here at the end there's no vertical component to that velocity. The jet's just going strictly horizontal. So the force in y required to hold the system steady is going to be the mass flow rate out times the velocity out in y minus 0, because there's no mass flow rate in for the y direction. The mass flow rate out, we know that the mass flow rate is 11.3 kilograms per second, and then we're going to multiply that by the velocity out in y. Well, the velocity is 6 meters per second, and it's down, so we have to give it a negative sign in front of that value, because down is, in our sign convention, going to be negative since up is positive. And then multiply that by the component of the velocity that is vertical. So we did cosine of 30 before, so that means we're going to have to do the sine of 30 degrees for this one. And the sine of 30 degrees is 0.5. And again, there's no mass flow rate in term for us to worry about. So the force in y required to hold the system steady is going to be negative 33.9 newtons, meaning that we would have to push down. The jet would cause that vane to rise if we weren't pushing down in the y direction. But the question asks the force of the water jet on vane. And so force of jet on vane is 9.08 newtons to the right and 33.9 newtons up. That's how hard the water jet is pushing to the right and up on that vane.
Mm-hmm. All right. This is a combination of both momentum equation and also continuity. You can see that we've got some black box. Inside of this black box is a series of vanes that we can't see, that we don't have to see, but it's redirecting flow. A jet of water comes in at 0.15 meters per second and a velocity of 60 meters per second. There's another jet over here that's coming in with a higher flow rate, 0.3 cubic meters per second, but a lower velocity, 30 meters per second. It's coming in. And then somewhere in here there are vanes that are directing some of the flow up and some of the flow down. And we're going to want to find out what forces are required to hold this system steady.
Alright, in this next example we are faced with a black box, and it's called a black box because we don't know and don't necessarily care what's happening inside the box. Inside the box, that's really our control surface. The interior is the control volume, but we do have some movement of jets that we're interested in. There's a jet of water that has a volumetric flow rate Q is 0.15 cubic meters per second, and we're given that the velocity in is 60 meters per second at that boundary. And there's a jet that's coming out right here and we know that the velocity of that jet is 15 meters per second, but we're not given the mass flow rate. There's another jet here that's coming in. We are given both the volumetric flow rate of 0.30 meters cubed per second, and the velocity is 30 meters per second. And then finally there's another exit stream here, and that exit stream we're given the flow rate to be 0.10 cubic meters per second, and the velocity is known to be 20 meters per second. We're going to have to apply the momentum expression in both the x and y direction. Just for simplicity, I've labeled each of these streams. I'm labeling this stream 1, and then we have stream 2, stream 3, and you guessed it, stream 4. Alright, let's start by looking at things in the x direction. Consider the momentum in x. So in the x direction, there's no mass flow out. There's only flow in the x direction. So that when we have the sum of the forces required to hold the system steady in the x direction, that's the mass flow rate out, velocity out in x. And by the way, I should say the sum of the components that are flowing out minus the sum of the components that are flowing in x. So there's no flow out in the x direction. You can see both stream 2 and stream 4 going into the black box. So that means that this term is 0. Let's take a look at the mass flow rates of stream 2 and stream 4. The mass flow rate for 2 is going to be this liquid has a specific gravity of 2.0. So for Sg of 2.0, then that means the density is 2,000 kilograms per cubic meter, because it's double the density of water. That's what Sg of 2.0 means. Okay, so the mass flow rate of stream 2 is going to be 2,000 kilograms per cubic meter times the flow rate of 0.30 cubic meters per second. The mass flow rate of stream 2 is 600 kilograms per second. Mass flow rate for stream 4 is likewise 2,000 kilograms per cubic meter. This time though, the volumetric flow rate is 0.15 cubic meters per second. Gives us a mass flow rate of 300 kilograms per second. Let's apply this in the x direction. Okay, so the force required to hold the system steady in the x direction is going to be the mass flow rate out, which there is none, minus, now doesn't matter which stream we consider first. Let's take a look at stream 2. Okay, so stream 2 has a mass flow rate of 300 kilograms per second, and we need to multiply that by the velocity for stream 2. So stream 2, 300, that was stream 4. So the mass flow rate of 4, and now let's do the velocity of 4. Now velocity of 4 is 60 meters per second, and that's to the right, so I'm leaving it as positive 60. Now we will do the mass flow rate of stream 2 and the velocity of stream 2. So the mass flow rate of stream 2 was 600 kilograms per second, and then the velocity is negative 30 meters per second. I should have made that as a plus. I guess it's a negative sign if you don't put the negative into here, but I think it's probably more consistent if I put the negative sign right by the velocity there. So It is the 300 kilograms per second at 60 meters per second from here at stream 4. And you can sort of tell that you'd have to push to the left in order to hold that steady. But then the other stream, you're going to have to push to the right to hold stream 2 steady. The force in the x direction, it's going to be canceling out, because 300 times 60 and 600 times 30 balances out. So in other words, those two jets sort of counteract each other, and no external force in the x direction is required to hold it steady, since the two jets counterbalance one another. Now we can consider the forces in the y direction. Alright, the sum of the forces in the y direction are equal to the sum of the mass flow rate out, velocity out in y, minus the sum of the mass flow rate in times the velocity in y. What don't we know yet? We don't know the mass flow rate of stream 3, but we do know that what goes in must come out, and so mass flow in equals mass flow out. So what's an in stream and what's an out stream? The mass flow rate of 2 plus the mass flow rate of 4 are equal to the mass flow rate of 1 plus the mass flow rate of 3. 3 is the only one that we don't know yet. So this becomes the mass flow rate of 3 is mass flow rate of 2 plus the mass flow rate of 4 minus the mass flow rate of 1. So that mass flow rate at 3 that we're trying to find is going to be negative 200 kilograms per second, which is calculated because we did know both the velocity and the, over here, if the flow rate is 0.1 cubic meters per second, the mass flow rate is going to be the density, which is 2,000 kilograms per cubic meter, times that 0.10 cubic meters per second. So that is 200 kilograms per second. Okay, so negative 200 kilograms per second. The negative because that is in the same outflow as mass 2, plus the 600 kilograms per second plus 300 kilograms per second. So the net mass flow is 700 kilograms per second. So that makes sense, right? That what flows out has to be balanced by what flows in. The total mass flow rate in is 900, and so we already were losing 200 kilograms per second out of 1, so therefore the mass flow rate coming out at 3 will be equal to 700 kilograms per second. Okay, so now we know the mass flow rates. Let's apply that into the momentum expression. The force in the y direction required to hold the system steady is going to be equal to the mass flow rate at 1 times the velocity at 1 plus the mass flow rate at 3 times the velocity at 3 minus 0, because there's no flow in this case. In the y direction there's only flow out. Okay, so the mass flow rate at 1 is that 200 kilograms per second that we calculated just a moment ago, and the velocity is up 20 meters per second. Since it's up, it's positive.
plus the mass flow rate at 3 we just found was 700 kilograms per second. And the velocity at 3, though, is negative 15 meters per second because it's down. This is 4,000 newtons, and this is 10,500 newtons. So the net force in Y required to hold the system steady is negative 6,500 newtons. So what force is required to hold the black box in place? The only force required to hold the black box in place is we have to push down at 6,500 newtons to hold the system steady. All right. Well, the U.S. Navy has a series of boats called LCACs. LCAC stands for Landing Craft Air Cushion. And these are pretty amazing machines. As you can see from the image there, they have the ability to land a full-size main battle tank, or 180 troops can be on the deck of it, or they could put 4 light armor vehicles, which are themselves pretty big machines. They can go about 80 miles per hour, which is a lot faster than an ordinary ship. An ordinary ship that's down in the water faces quite a bit of resistance to moving at that speed, but an LCAC, by contrast, floats above the water. The curtain of the LCAC, when it's operating, is actually up above the water so that it has much less resistance to movement, and that's why it's able to achieve such a high velocity. And that comes at a cost, though. It burns 1,000 gallons of fuel per hour. Think about what your fuel costs would be. The engines in these LCACs, if I remember correctly, the engines are able to burn a variety of fuels, but most of the time what they'll put into it is jet fuel. It's actually a gas turbine, and jet fuel is very expensive because it has a very high octane. Jet fuel doesn't combust as easily. It burns at a higher temperature. And so, like, I was up at the Tri-State Airport a couple of months ago, and they have a flight operations office off the main building there, and they were charging something like $6 a gallon for jet fuel at that point. And so if you think it's $6,000 per hour is what you're spending to run one of those things. But when you need to take a tank inshore at 80 miles per hour, then it's your best option, I guess. So it's an interesting from a fluid mechanics standpoint as well. Let's take a look at this video, and then we'll talk about the way that the LCAC operates. I was hoping that it'd show it going off at 80 miles an hour, but I don't think... let's just try this one. I can't resist. Looks like they're going fast on this one. Pretty quick. Not 80. How do those things float? Look at that big truck that's coming off of it. How does something like that float? Yeah? Okay, precisely. That's exactly it. The force of the air going down is greater than the weight.
Hello, I'm Patrick Kennedy. Last year, more of our military members died by suicide than from combat. Anyone can experience stress after a traumatic event. It's up to each of us to let our...
It's just to get troops and equipment on shore quickly. Yep. Nope. Nope, but they're fast, and they can clear obstacles too. Like you know, an ordinary boat that's landing troops on shore would have to stop at the beach because it has to only go where the water is. But this could go a mile inland if it had a path free of obstacles. So it can establish a much deeper beachhead very quickly.
Let's take a look at an example that uses this hovercraft as a starting point. We're going to work through this example and try and calculate four things. First of all, just a simple drawing of the LCAC, and I'd like you to try this without watching what I do. I'd like you to sketch, based on momentum, how you think this thing works. How is it able to lift up the load, and how is it able to achieve a forward movement? So do a little sketch in the margin of your notes. Secondly, I'd like you to calculate the air pressure required in order to lift the fully loaded LCAC up off of the ground or up off of the water. Fully loaded, it's 185,000 kilograms, and the dimensions are 26.4 meters long, 14.3 meters wide. And those are actually real-world figures that I was able to look up. Third, we're going to go through and calculate the thrust of an LCAC when each of the propellers is 3.6 meters in diameter, and again, that's a real-world figure. They're very large propellers. And in order to calculate the thrust using the momentum equation, you'll need to assume density of the air in order to turn that into a mass flow rate. And so the typical density for air is 1.2 kilograms per cubic meter. And then also you're going to assume that the velocity of the air coming off the propeller is 150 meters per second. And then finally, you'll calculate some forward thrust in step 3. Use that in step 4 in order to find out the acceleration of an LCAC. You know, when it's stopped and those propellers turn on to start moving it forward, how quickly can it potentially accelerate? In this example, we're taking a look at a hovercraft called an LCAC, and we're going to do some calculations based on the momentum principle. And first of all, need to draw a sketch of what's happening. Alright, so a conceptual sketch. If we simplify the hovercraft to look like basically just a box with this rubberized skirt that the air is coming down out of, and it's hovering on top of some land. It has weight based on the known mass of the hovercraft and whatever equipment's in it. And let's draw, by the way, a control surface. To hold the hovercraft steady, if it had like a fan system on top that's blowing air this way, we would want to know the mass flow rate of the air and the velocity of the air, and then this is the force that would be required to hold the system steady. So this is just a basic idea of what the hovercraft looks like. It's the air coming down from the skirt that counteracts the weight force. And so now in the second part of the example, we're going to take a look at what pressure is required under the skirt in this area, what pressure is required to hold up the LCAC. And we can first of all look at this to find out what is the weight of the LCAC. And the weight is related to the mass times the gravitational acceleration. We're given in the problem statement that this hovercraft weighs 185,000 kilograms, which is pretty heavy. And G is 9.81 meters per second squared. And so the weight of this hovercraft is 1,814,850 newtons. It's given in the problem statement that if we look down from above on the LCAC, it is 14.3 meters wide and 26.4 meters long. And so the area is just the product of those two numbers. So the area is 377.52 square meters. And the reason why we want to know the area is that this pressure in the skirt, underneath the skirt area that's actually lifting up the hovercraft, is simply calculated by F is pressure times area. In other words, we can find the pressure by calculating the force. In this case, the force is the weight that's being lifted up, and divide that by the cross-sectional area. So the weight divided by the area. And so the pressure is going to be 1,814,850 newtons divided by the cross-sectional area of 377.52 meters squared. And so the pressure is 4807 newtons per meter squared. And since we're more familiar with traditional units in the U.S., that may not, register for, we're not maybe as acquainted with what that means. And so I'll just point out that that's equivalent to approximately 0.7 psi, which is not a very big pressure increase. The reason why it's able to lift something so heavy is because that's actually a very large cross-sectional area that the hovercraft uses. In the third part of the example, we want to find the thrust, and we're given some information about the LCAC. We say, assume that there are two propellers. Each of the propellers has a diameter of 3.6 meters, and the air density is 1.2 kilograms per cubic meter, which is sort of a typical atmospheric air density. And then assume that the air coming off of the propellers is 150 meters per second. So if we go back up here into part 1, we're assuming that the velocity of the air is 150 meters per second. Okay. So first of all, I want to find the cross-sectional area of that air jet that's coming off of here. The diameter of the propellers, D, is 3.6 meters. And so the cross-sectional area of the propellers is pi d squared divided by 4. And so that is 10.18 meters squared for each of them. And there are two propellers for thrust on the LCAC. Now let's remind ourselves about the momentum principle. Remember, the momentum principle says that the sum of the forces required to hold the system steady in the x direction are equal to the sum of the mass flow through the control surface, mass flow rate out, velocity out in the x direction, minus the mass flow rate in times the velocity in the x direction. Just to simplify things, let's say that the LCAC isn't moving yet, because if we go back up here to the diagram you can see that there actually will be air coming into the control volume once the LCAC is moving. But when it's stationary, we'll assume that the air that's on the upstream end of the propeller is stationary. So just to begin and to simplify, we'll say assume that the velocity of the air in the x direction is 0. And that would be different once it gets moving. So we need to find the mass flow rate of the air. So the mass flow rate of the air that's going out of the control volume because of that propeller is going to be the density of the air times the volumetric flow rate. And of course we know that volumetric flow rate is the cross-sectional area times the velocity. So 1.2 kilograms per cubic meter is the density of the air, and then the cross-sectional area for each one of those blades is 10.18 square meters. And then we have the velocity of the air going out is 150 meters per second. And that gives us a mass flow rate for the air going out is 1832 kilograms per second, and that's each. Because remember, there are 2 of those thrusters. So how much force is that? If we go back up here to the momentum expression, the force required to hold the system steady, if we didn't want it to move at all, then it's going to be the mass flow rate of 1832 kilograms per second, and the velocity out of 150 meters per second. And there's no mass flow rate in velocity in term because we assume that the velocity of the air going into the control surfaces through the control surfaces is 0. So the force is 274,826 newtons each. And so if we double that, so multiplying it by 2, then the total force for the 2 thrusters is 549,653 newtons. And finally, in part 4 of this example, it's asking how quickly can an LCAC accelerate when it's fully loaded. And this will be its initial acceleration, because remember, as soon as it starts moving, then the velocity in isn't 0 anymore, and that's going to reduce the effective thrust. And so it has its most thrust when it's stopped and just barely starting to accelerate. The way that we're going to calculate the acceleration is F equals ma. We've got a force. If we don't apply this force to hold it steady, if we get rid of that force to hold the system steady, then the system is going to begin accelerating. We can rearrange that. The acceleration is the force divided by the mass. And so the force that we knew for the 2 is 549,653 kilogram times meter per second squared. And I wrote it like that. Up here we had expressed the force in terms of newtons, but a newton is a kilogram meters per second squared. I wrote it like that just to make it more obvious how the units are canceling out. Once I divide by the mass of the system, it's fully loaded 185,000 kilograms. And so the acceleration is 2.97 meters per second squared. That's a pretty healthy clip. That's accelerating at about 0.3 g. Just to put that in perspective, a Ford Mustang, when Ford Mustang is going from 0 to 60 miles per hour, it does that in about 4.9 seconds. To achieve that, it's 0.56 g. And so this isn't accelerating as fast as a Ford Mustang, but at the same time it weighs 185,000 kilograms, and so that's still a pretty quick acceleration.